Okay, then let's start with coordination compounds, chemistry. Okay, what are coordination compounds? The first question is what are coordination compounds? Compounds containing a central metal ion which is surrounded by number of ligands linked through coordinate bonds are called as coordination compounds. The simple definition of coordination compounds is compounds containing a central metal ion which is surrounded by number of ligands linked through coordinate bond are known as coordination compounds. That's about coordination compounds. Compounds containing a central metal ion which is surrounded by number of ligands. It can be one ligand, two ligand, or many more. Linked through coordinate bonds. Coordinate bonds meaning the ligands itself will donate the electron pair. There will be no donation from the central metal ion. The ligands, most of the cases, will donate the lone electron pair into the vacant d orbitals of the central metal ion. This will form a coordinate bond with the between the central metal ion and the ligand. Example we can take potassium hexacyanide ferrate. We will see the nomenclature of these as well. Then these are a few examples. Here the name, it's not official name but common name, it is potassium ferrocyanide. Potassium ferricyanide. That is potassium ferrocyanide and ferricyanide. That's about a few examples. Now, before starting the coordination compounds, even though the name of the chapter is coordination compounds, we will see two main categories. The first one is a simple introduction for us, not much depth, that is about double salts. What is a double salt? And some examples are given, which, although very less information, it is very important to remember this. A double salt is a salt formed by two simple salt when it is dissolved in water is known as double salts. A salt, or it's more correct to say a double salt, is formed by two simple salts. We know simple salts like NaCl, KCl, etc. Two simple salts. A double salt is formed by two or more simple salts. And I like a specific property of double salt is that when double salt dissolved in water, it will give, it dissociates to give all the constituents present in it. Like this is a property that is different from the coordination compounds. A double salt, like a normal salt, when dissolved in water, it will give all the individual constituents. For example, if we dissolve NaCl in water, we will get Na plus and Cl minus, or KCl in water, we will get K plus and Cl minus. Similarly, when we dissolve a double salt in water, we will get all its individual ion components. There are few important examples for double salt. One, potash alum. It is K2SO4, Al2SO4, thrice, and 24H2O. K2SO4, potassium sulfate, aluminum sulfate, and 24 water molecules. Total, it's called as potash alum. And second example we can take ferrous ammonium sulfate. This is also double salt, commonly called as FAS. It's also called as Mohr's salt, ferrous ammonium sulfate, FAS, and Mohr's salt. The most common name is Mohr's salt. Its formula is iron sulfate, ferrous sulfate, ammonium sulfate, and 6H2O. It might seem very hard to remember these names, but it is kind of okay. It is simple. Both of these salts have sulfate in them, and we know the sulfate valency is 2. I mean, it can accept 2 electrons. So potassium, it is 1, so 2 potassium and 1 sulfate. Aluminium, it is 3, so Al2SO4 thrice, and 24H2O we need to remember. As for Mohr's salt, if you remember the name FAS, we can easily write it as ferrous sulfate, ammonium sulfate, and water. 6 water should be remembered. Potash alum, in the name itself there is potassium and aluminium, so potassium sulfate and aluminum sulfate and 24H2O. As for Mohr's salt, it is called as FAS, ferrous ammonium sulfate. So there will be ferrous sulfate, and we are talking about ferrous sulfate. Ferrous and ferric, there is a difference. Ferrous is +2 oxidation state of ion. Ferric is +3 oxidation state of ion. So ferrous sulfate is FeSO4. Ferric sulfate is Fe2SO4 thrice. That is not here. Here we only have ferrous sulfate. So FeSO4, then ammonium sulfate, then 6H2O. Then if we see some differences between complex salt and double salt, let's just write them so we can get an idea. Double salt, complex salt, or coordination compound. Both are the same thing. Double salt loses identity in solution, meaning it will not stay as a salt, a complete salt. We saw FAS. After it dissolves in water, FAS will not remain as FeSO4 and H42SO4. It will dissolve to give Fe2 plus, SO42 minus, NH4 plus, and SO42 minus. That means loses identity. But complex salt is special because it does not lose identity, retains identity. This is the speciality of complex salt. It is a very important character. As for double salt, one more, does not have coordinate bonds. It's more ionic, just like normal salts. This does not have coordinate bonds. Coordination or coordinate bonds is once again not specifically a specialty of coordinate compounds, but easy to remember, like coordinate compounds because they have coordinate bonds, coordination compounds because they have coordinate bonds. Very simple, has coordinates bond, has coordinate bonds. We saw that definition of coordination compounds. They are central metal atom which is surrounded by ligands forms coordinate bonds with them. That is itself is a coordination compound. It is stable in aqueous state, I mean stable in solid state, meaning it will retain its identity in solid state. It is stable in both aqueous and solid state, as in aqueous also it will retain identity, in solid also it will retain identity. This one shows normal valency, meaning its ionic character shows normal valency, but there we involve vacant d orbital, so the valency will, the normal idea will be gone. It shows, according to Werner, it shows coordination compounds or complex salts show primary valency, that is oxidation number, and secondary valency, that is coordination number. It is different from normal valency. Okay, that's about that. At the start of NCRT, we got the importance of coordination compounds, like what is the significance, or like where can we find coordination compounds in our nature, in our surroundings, in our environment. What is the most important role played by coordination compounds or complexes? So there are a few important examples which we need to remember. Coordination compounds in nature, in we all know about hemoglobin. Hopefully, hemoglobin is a pigment which is present in our blood, in our red blood cells, which helps in carrying of oxygen. It contains four iron atoms where oxygen will bind to, forming oxyhemoglobin. We don't need that much detail, but we just need to know hemoglobin is a complex of iron. It's a iron complex. Then we all know about chlorophyll. Chlorophyll, which helps in photosynthesis, the most uh, the green color pigment present in almost all of the plants, which helps in their photosynthesis and provides food for the whole biosphere. It is a salt of, I mean, it's a complex salt of magnesium. It is a complex of magnesium. And then we have vitamin B12. This is a complex of cobalt. Hemoglobin, it is easy to remember, iron. Chlorophyll, it is a complex of magnesium. Vitamin B12, it is a complex of cobalt. Iron, magnesium, cobalt, hemoglobin, chlorophyll, and vitamin B12. These are some important names which we should remember. Okay, coming to the main next theory here. It is Werner's theory. Werner's theory, let's see the postulates. The first postulate is that a metal atom in a coordination compound, I'll just write CC, coordination compound, has two types of valency. First one, it is primary valency, and secondary valency. This primary valency is nothing but the oxidation number. Secondary valency is the coordination number. Primary valency is ionizable and satisfied only by negative ions, and it is non-directional. Then secondary valency is satisfied by either neutral or negative ions. They are called as ligands. Primary valency is oxidation state of the central metal atom. Secondary valency is the coordination number. Primary valency may be variable, but secondary valency is fixed. Primary valency non-directional, secondary valency directional. Hence, or because of that reason, complexes give different geometries. For example, if coordination number is 6, it gives a octahedral geometry. If coordination number is 4, in that case it will give a tetrahedral geometry. Let's see the postulates again. Werner's theory, a metal compound in a coordination compound has two types of valencies. It is primary valency and secondary valency. Primary valency is ionizable and it is satisfied only by negative ions. Ionizable meaning it has a charge, has a specific charge on it, and it is satisfied because it has a positive charge. Normally metal ions is have a positive charge, so it is satisfied only by negative ions, and hence primary valency is oxidation number and is ionizable and satisfied only by negative ions. Secondary valency is different. It can be satisfied by both neutral or negative ions. They are called as ligands. These ligands will satisfy the secondary valency by donating electron pair into the vacant d orbitals of the central metal atom. Primary valency may be variable, it can be changing, like we saw before in a complex example like potassium ferrocyanide and potassium ferricyanide, where iron having +2 and +3 states. So primary valency may change. Primary valency is nothing but the oxidation number and it may change, but for a specific metal secondary valency is fixed because the coordination number will remain fixed. Cobalt can accommodate 6 ligands or 6 electron pairs, so it will remain fixed. No matter if it was a weak ligand or a strong ligand, it can only accommodate six ligands or six pairs of electron. Primary valency is non-directional, secondary valency is directional. Primary valency has only attraction and repulsion, but secondary valency it is directional. It provides shape to the complexes. Like why it is directional, meaning secondary valence is a coordination number, meaning the ligands which are attaching, ligands will attach in a certain geometry to minimize repulsion. So it is directional. To the they will be arranged in a shape having least repulsion. In case if it was coordination number is 6, it will arrange in an octahedral structure. If it coordination number was 4, it will arrange in a tetrahedral structure. Which type of ion satisfies the primary valency of a complex? Negative ions are anions. Okay, there is a certain experiment here performed by Werner. I will directly write the question asked based on that experiment. The formula. Okay, there is a certain compound. Let's go with first one. PDCl2 4NH3. Now, if this compound was reacting with uh, excess AgNO3, then what could be the number of AgCl molecules it could liberate? So if we want to write that, we need to first write the complex formula of this coordination formula of this compound, which is not this one. This is Werner's formula, Werner's way of writing the formula. This is the compound. So PDNH4 thrice and Cl2 outside. This thing here is known as the coordination sphere. This thing outside is known as the ionic sphere. And this palladium inside here is known as the central metal ion. And NH4 is the ligands. When this compound is dissolved in water, it will dissociate to give PDNH4, NH3 4 times plus 2 plus 2Cl minus. Hence, the identity of the coordination sphere is retained. This is the reason coordination compounds retain their identity. So, when this compound reacts with excess of AgNO3, it will give 2 moles of AgCl, 2 moles of AgCl because it has two free chloride ions. Now let's go to the next compound. Next is NiCl2 6H2O. Here nickel will form this complex, or wait a second, I think this information is already given for us. Okay, yeah, it is given for us already. It is said that 2 moles will form, so based on that information we need to find this formula. If it said only 1 mole will form instead of 2, then 1 Cl will be inside. one H2O will be outside. But since they gave 2, that means that 2Cl should be outside, and coordination number of nickel is 6. Third one, Pt platinum Cl4, 2HCl, it will form 0. Then next, COCl3, 4NH3, coordination number of cobalt is 6, and they gave that 1 mole of AgCl is formed. That probably means that only 1 mole of Cl is outside. Then PtCl2, 2NH3, here as well it is 0. So the question is, we need to find the secondary valencies of the specific ions. So the secondary valencies of these specific ions we need to find. Okay, in this case PdCl2 4NH3, since I already told the secondary valency of this. Since 2 AgCl is released, it is Pd, I mean palladium, then tetraamine, meaning 4 ammonia inside. So the coordination number of this compound is 4, since there are 4 ligands inside. That is the maximum it can accommodate. Then in case of this, since 6 water already are inside, so it is 6 is the coordination number of nickel. Then platinum chloride, since like both this Cl and Cl from HCl, actually I'll check this later. Now coming to cobalt chloride, if we need to write the formula, and since 1 mole of AgCl is liberated, 1 chloride atom should be outside, remaining everything should be inside. Cobalt, Cl2, NH34, Cl outside. This is the formula. Now if we see, there are a total of 6 ligands inside, so coordination number is 6. In case of this one, since it's liberating 0 chloride molecules, that means that all of the chlorine molecules are inside, and that is Cl2 NH3 twice. This compound might seem familiar. It forms this compound is actually can form 2 types. In isomerism, we will see cisplatin and transplatin. Cisplatin is used in cancer treatment. Then that's all for this question. The coordination of number of this compound is Cn equals 4, because 4 ligands are inside. Okay, now let's see the merits, I mean demerits of, or limitations of Werner's theory. Limitations of Werner's theory. Demerits, limitations, same thing. Theory does not explain how a ligand can satisfy both primary and secondary valency of a central metal ion. It does not explain how like both primary and secondary are satisfied by a ligand. Secondary valencies are satisfied by a ligand. It does not offer electronic interpretation of formation of complex ion. It does not explain magnetic and optical properties of coordination compounds. These are the three limitations of Werner's theory. Let's see them again. The theory does not explain how ligand can satisfy primary and secondary valency at the same time. It does not offer electronic interpretation of formation of complex ions, maybe something dealing with the charges. Then it does not explain magnetic and optical properties of coordination compounds. First thing, does not explain how a ligand can satisfy primary and secondary valencies, does not offer electronic interpretation, does not explain magnetic and optical properties. Okay, let's come to definitions and of some important terms of coordination compounds. We talked about, I gave a brief introduction about what is a coordinate bond before, but I will write the definition here. Coordinate bond, or it is also called as dative bond, coordinate bond is also called as dative bond. It is a bond, one atom slash group donates lone pair of electron. Then we know the definition of this is a coordinate bond where one atom group donates lone pair of electron. Then what is central metal atom or ion? The metal atom or ion surrounded by number of neutral molecules or negative ions. Ligands in a complex or a coordination compound is called as a central metal ion. In a complex compound, central metal atom acts as a Lewis acid because it acts as an electron pair acceptor. CMI acts as Lewis acid because electron pair acceptor. What is a coordination entity or a coordination sphere? A central metal atom bounded by fixed number of ligands with geometrical arrangement is called as coordination entity. I showed you in the palladium, I think some before case, the 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 whole compound inside the square bracket is known as a coordination entity or a coordination sphere. It has the central metal ion and the ligands surrounding it in a and forming a specific geometry. Then what are ligands? Ligands are Ions are molecules which can donate one or more lone pair of electrons to central metal ion through a coordinate bond in a complex compound. Complex compound ligands act as Lewis base. Ligands, electron pair donor, can donate one or more pair of electron to central metal atom, act as Lewis base, electron pair donor. That's about ligands. Then types of ligands. We can classify ligands based on their denticity, the number of electron pairs they will donate. Monodentate ligand, denticity 1, can donate one pair of electron. In case of bidentate ligand, as the name says, can donate two pair of electron. Then we have tridentate, tetradentate, pentadentate, and so on. But let's just write polydentate ligand, many pair of electron. Then we have ambidentate ligand. This is a ligand which has a special characteristic, meaning it has two donors in the same. The ligand will have two donors, but both of them will not donate at the same time. Each donor will donate at a single time. They will not donate simultaneously. This is known as an ambidentate ligand. It has two or more donors, but not all of them will donate. Only one of them will donate. It has many donors, but will act as a monodentate ligand. We saw what are monodentate ligands. Ligands which can donate only one lone pair of electron to the central metal ion are known as monodentate ligands. For example, we have ammonia, water, carbonyl, nitrosyl, etc. Or negatively charged, these are neutral. If you want negatively charged, then we have Cn minus, cyanido, chlorido, bromido, iodido, fluorido, etc. Then thiocyanato, acetato, hydroxido, oxo, and so on. I will write this later. Then we also have positively charged ligands like NO2 plus, NO2 plus, NO plus. NO2 plus is nitronium ion. NO plus is nitrosonium ion. These are also monodentate ligand. All these are monodentate ligands. As for bidentate ligands, what are bidentate? We can also call them as didentate, didentate, or bidentate, bidentate and didentate. The ligands which can donate two pairs of electrons to the central metal atom are called as bidentate ligands. Example, if we have, we can take oxalato, C2O4 2 minus, this is known as oxalato. Then we have ethane 1 comma 2 diamine, we represent it as En, ethane 1 comma 2 diamine. I'll write the structures later. Actually, let's write the structures now itself. Let's write the bidentate ligand structures. We have oxalato, or we don't, we can say it's oxalate ion. Oxalate ion, C2O4, 2 minus. There will be carbon bonding like this. This will be the structure of the oxalato ion. These two oxygen having the lone pair of electron are the donors. This negative charge, right, that one they will donate to the central metal ion. Now coming to ethane 1, 2 diamine. Very simple structure. First we write two carbons, eth, then nitrogen attached here. Nitrogen are the donors here because they have lone pair of electron. These two are the donors. Here we have oxygen with the negative charge are donors. Here nitrogen with the lone pair are the donors, represented as En, ethane 1, 2 diamine. Then coming to polydentate ligands, example is EDTA. EDTA is ethylene diamine tetraacetate ion. Polydentate ligands, let's see the definition. Polydentate ligands are the ligands which can donate many lone pairs of electrons to the central metal ion to form complex are called polydentate ligands. Basically they are saying they can donate many number of lone pair of electrons simultaneously. They can donate many number of ligands, I mean electron pairs simultaneously. Only this one ligand EDTA can donate 6 pairs of electrons. That is a polydentate ligand. Let's see the structure of EDTA. EDTA, ethylene, diamine, tetraacetate. We take two carbons, two nitrogens, similar to ethane 1, 2 diamine, but instead of hydrogens here, we will have here acetate group. This is the structure of EDTA. The donors are these two nitrogens and these four oxygens. These are the donors. 6 donors. EDTA is a hexadentate ligand. Hexadenticity. Denticity is the number of denticity of a specific ligand is the number of electron lone pairs it can donate. Okay, there seems to be a mistake here. Just a minute. This is, there should be a CH3 group here. Let me just correct it. CH2 COO minus, CH2 COO minus, CH2 COO minus, CH2 COO minus. It is ethylene diamine tetraacetate. These four oxygens are the donors, and these two nitrogens are also the donors. Now coming to the next topic, chelating ligand or chelating ligand. Chelating or chelating ligand, whatever it might be. It is when a di or polydentate ligand that uses two or more donor atoms to bind a single metal ion is called chelating ligand. Example is EDTA. Basically, if we have a polydentate ligand, it has many donor atoms as we saw before, and these donor atoms will bind to a single central metal ion. If that is the case, it will form rings around the central metal ion. It will form a ring with the central metal ion. This is known as chelating. What is a chelating complex? A complex in which a polydentate ligand is bonded to a central metal ion with two or more bonds forming rings is called as a chelating complex. If there is a ring, if there is a multiple donation to the central metal ion, that is known as chelating or chelation. Now coming to ambidentate ligands. The ligands containing one or more donor atoms which can link through only one donor atom at one time are called as ambidentate. Contain more than one donor atom but donate only one electron pair at a time is called ambidentate ligand. Example, we have cyanide group. For example, if we have a metal, the cyanide structure is something like this. So there will be a lone pair. I think there will be a negative charge on carbon and lone pair on nitrogen. And it can either link through carbon like this, or if M is a metal or a central metal ion, it can link through nitrogen. This is called as cyanido. This is called as isocyanido. There are few more examples. There is nitro group, NO2 minus. The structure is something like this. It can bond through lone pair in nitrogen or negative charge on oxygen. These both are donors. It is in resonance, so not only this oxygen, even this oxygen can be a donor. So it can attack the metal like this. From nitrogen, or it can attack through oxygen, oxygen's negative charge. This is known as nitro. This is known as nitrito. Then we have thiocyanate, SCN minus. Structure is something like this. Actually, let's not write the structure, it's not needed. Metal, it can attack through sulfur, or it can attack through nitrogen. This is known as thiocyanato. This is known as isothiocyanato. That is a few examples of ambidentate ligands. Now we know the definition of denticity. Denticity is the number of ligating groups present in a ligand is called as denticity. Example is denticity of oxalate ion is 2, denticity of En ion is 2, denticity of EDTA is 6 hexadentate. Okay, let's see the definition again. Denticity, number of ligating groups in a ligand is called denticity. What is the coordination number? Number of monodentate ligands or number of coordinate bonds present in a complex is called as coordination number. Coordination number, number of coordinate bonds, coordinate bonds present in a complex is coordination number. What is a coordination sphere? The metal atom and the ligands which are enclosed in a square bracket is known as coordination sphere. There is a special one more term, a coordination polyhedron. Coordination What is this coordination polyhedron? Spatial arrangement of ligands around the central metal atom or the shape of the complex is called coordination polyhedron. Arrangement of ligands around a central metal ion or geometrical shape of complex is known as coordination polyhedron. Hard sounding name but simple sounding definition. Example, for example, we have nickel tetracarbonyl. Here it has coordination number 4. So its polyhedron is tetrahedral. In case of cobalt NH3 6 hexamine cobalt ion, its coordination number is 6, so octahedral. Then we have hexamine copper. This one is not tetrahedral or octahedral. It is square planar, meaning it will arrange something like this in the plane. This is a square planar. This is not a bonding. It's just me showing the geometry more clearly. Tetrahedral is something like this. If we go for this complex, which was tetrahedral nickel carbonyl structure will be something like this. Where all these angles will be same. It will be 109 degree or something like that. Then as for octahedral, it will be something like this. It will be a mix of both tetrahedral and octahedral. I mean square planar and tetrahedral. This is the octahedral structure. We will have 8 faces. Okay, that's about polyhedron, coordination polyhedron. Then there are two simple yet important complex, I mean, information, that is homoleptic and heteroleptic complexes. Very simple. Homoleptic meaning the compounds will have same kind of ligands. Heteroleptic meaning the compounds will have different kind of ligands. Example, we have CONH3 6 times 3 plus, or we can take Cl3. Here inside the coordination entity we only have NH3. Only NH3 is the ligand. Only one type of ligand is there, so homoleptic. One more example, ferric cyanide. K4 ferric cyanide. Here as well the inside only cyanide is present, so it is homoleptic complex. For heteroleptic complex example, we have this one. This has ammonia and chloride inside the complex. It is heteroleptic complex since it has two different kind of ligands. Or we can take this is also heteroleptic complex. It has three different kinds of ligand inside it. That's about homoleptic and heteroleptic complex. Let's see the definition. Homoleptic complexes are complexes in which the central metal ion is surrounded by only one type of ligand. They are called as homoleptic complexes. What are heteroleptic complexes? Complexes in which central metal ion is surrounded by more than one type of ligand or are called as heteroleptic complexes. Okay, coming to the next topic, what is a complex ion? What is a complex ion? Complex ion, like if we see, I told about dissociation. This one, if it dissociate, it will dissociate into coordination entity plus 3 charge and 3 Cl minus ions. This charged complex is known as complex ion. It is a charged species containing central metal ion surrounded by ligands, that is known as a complex ion. What is primary valency or oxidation state of a central metal atom? The charge on the central metal atom in a complex is called primary valency or oxidation state or oxidation number. It is quite simple to calculate the oxidation number. Let's do some examples of calculating the oxidation number. Example, K4 FeCN6. Here the total charge on the complex we can find by K4. Single potassium has +1 charge, so 4 should have +4. +4 is the total charge of the ionic sphere. Then -4 should be the charge on the complex, so -4. -4 is the charge on the complex. Okay, so -4 is the charge on complex. Then ion charge, we can take it as X, plus charge of single cyanide is -1. 6 times -1 is equals to -4. X -6, which is equals to -4. X, which is equals to +2. Charge on ion is +2. So we represent it as ion 2. It is a ferrous ion. Then similarly, we can find the oxidation number very simply. Like, it is easy, so I will not be doing much about it. We have different kind of complexes. In this case, it is a anionic complex. Here the charge on the complex is negative, so it's an anionic complex. This is an anionic complex. We have neutral complex as well. Neutral complex as well, or even cationic complexes. There are 3 types of complexes. Complexes can be cationic, positive charge on complex; anionic, negative charge on complex; neutral, no charge on complex. What are cationic complexes? Positive charge will be there on in a complex. For example, we can take CuNH3 4 times. This complex has a positive charge of +2. This is known as the cupramonium complex. Or cobalt NH36. This has a +3 charge. It is called as a hexamine cobalt complex. Then as for anionic complexes, this is an example for an anionic complex. It has a -4 charge on the complex. It is ferrocyanide ion. We can see ferricyanide ion if there is 3 here. Then as for neutral complexes, we have nickel tetracarbonyl. This complex has no charge. Or iron pentacarbonyl. This complex also has no charge. That's about the types of complexes and examples. Now let's go to the nomenclature of coordination compounds. Nomenclature of coordination compounds. Okay, the first rule, always name anion, cation before the anion. It doesn't matter if the complex is anion or complex is cation, or even the ion, even the simple ion can be a cation or anion. It doesn't matter. Whatever has a positive charge, that one we should name first. I'll read out the full statement. To name a coordination compound, no matter the whether the complex ion is a cation or anion, always name the cation before the anion. Always name the cation before the anion. This is the first rule. Second, while naming anionic ligands, the terminal E of the ligand is replaced by O, that is ide. As let's see a few names. Just a minute. Okay, let's continue. Nomenclature, rules of nomenclature. Rules of nomenclature. First one, cation should be named first. Always. Second one, we have specific names. We don't call chloride. We call it as chlorido and so on. So let's write them. I'll just write anionic ligands as negative ligands. Names, neutral ligands, and names. Okay, let's start with for anionic ligands. Bromine, bromide is called as bromido. It's not necessarily a capital letter. Fluoride, fluorido, chloride, chlorido, hydroxide, hydroxido, cyanide, cyanido, C2O4 minus, oxalate, oxalato, then CO3 2 minus, carbonato, carbonate is called as carbonato, CH3COO minus, acetate, acetato, NO2 minus, N-nitrito or nitrito N, ONO, nitrito O, then SCN minus, thiocyanato S, then if we write NCS, thiocyanato N, these are a few names then of anionic ligands. Then coming to neutral ligands, NH3 we call in the naming amine, double MINE. H2O has a name aqua. NO nitrosyl. CO is carbonyl. C5H5N, it is pyridine. Ethane 1 comma 2 diamine, we name it as En, or ethane 1 comma 2 diamine, you just write it ethane 1 comma 2 diamine. Then pph3, this is triphenyl phosphine, this is phosphorus, this is phenyl rings, benzene rings, triphenyl phosphine. These are a few cationic, negative anionic ligands and neutral ligands. Now coming to third rule, Greek prefixes are used to designate the number of each type of ligand. In the complexes, the prefixes di or bi, tri, tetra, penta, hexa, etc. are used to indicate the number of monodentate ligands. If the ligand already contains a Greek prefix, like in case of ethylene diamine, or if it is a polydentate ligand, the prefixes bis, tris, tetrakis, pentakis are used. What this means is, for example, if there are monodentate ligands, in case of, we will see the naming later, di, tri, tetra, penta, hexa, used for monodentate ligands. Bis, tris, used when ligand already has Greek prefix or is a polydentate ligand. Then fourth rule, after naming the complexes, the central metal, if the complex ion is a cation, the metal is named with the normal name. But if it is, for example, an anionic complex, suffix 8 is used for central metal ion, only if it is an anionic complex. Like if it is an anionic complex, ion, normally if it's a cationic or neutral complexes, we use ion. But if it is an anionic complex, we call it as ferrate. If it is normal copper, we call it as copper. If it is anionic complex, cuprate. Lead normal. If it is anionic, plumbate. If it is silver normal, if it is anionic, argentate. Cold normal, aurate anionic complex. Tin normal, stannate anionic complex. Then fifth rule, After central metal, its oxidation state is mentioned in Roman number. Example, cobalt 3 or iron or ferrate if it's an anionic complex 2, etc. Sixth rule, to name a neutral complex molecule, follow the rules of naming a complex cation. To name neutral complex, follow rules of naming cationic complex. These are the 6 rules. First rule, let's see the rule. Cation should always be named first. It can be either complex may be cation or complex may be anion, but cation should be named first. Then two special names should be used. Bromine, bromido should be used. Fluorine, fluorido should be used, and so on. These are the prefixes, Greek prefixes to indicate the number of monodentate ligands. These are the Greek prefixes used to indicate number of polydentate ligands or ligands already having prefixes in their names. And for anionic complexes, we use a suffix ATE to convert iron to ferrate, copper to cuprate, and lead to plumbate, and so on. And we represent the oxidation number of central metal atom in Roman number in brackets after the name of the central metal ion. And to name neutral complexes, we follow the rules of naming cationic complexes. I won't do much naming here. Let's just do some one or two examples. If we go with cobalt NH35 CO3 Cl, here chlorine is negative, this complex is positive, so we go with naming the complex first. Central metal should come last. First, these should follow the alphabetical order. This is amine first alphabetically, then this is carbonato according to alphabetically it is second, so and 5 amine, so penta amine double M single carbonato, so carbonato. There is no need for spaces here, it should be without spaces. After the ligands are named, cobalt, oxidation number, charge of anion is +1, carbonato charge is -2, x -2 is equals to 1, x equals 3, so cobalt oxidation number is 3. Then cationic complex is named. Now coming to the ionic sphere, little space, chloride, pentaamine carbonato cobalt 3 chloride. This is the name of the complex. Let's do one more. Platinum NH3 twice, Cl NH2 CH3 Cl. Here we have 4 ligands. One ligand, 2 ligands are amines. One ligand is chloride. One more ligand is methylamine. Methylamine should be in bracket. Then the outer is chloride is negative, charge on the complex is positive. So first positive should be named first. Methyl chloride amine. Amine will come first alphabetically, then chloride alphabetically, then methylamine alphabetically. So biamine chloride chlorido, methylamine, since positive anionic, cationic complex, just platinum. Then coordination number, it should be 2 chloride. We don't need to mention if it is single chloride, double chloride, doesn't need to be mentioned. Just chloride, even if it's 3 chloride, 4 chloride, or 2 chloride. Then let's go with some anionic species. Let's go with a chelating ligand as well. K3 FeC2O4 thrice. Now charge on the ionic sphere is +3. Each will have +1, so 3 potassium, so +3. Then this will have -3. Oxidation number of ion X minus 3 into, +3 into, because 3 ligands, charge of each ligand is -2, which is equals to -3. X, which is equals to +3. -6, that it will go that side. 6 minus 3, 3. So that the oxidation number of ion is 3. Now this is anionic complex. First cation should be named. So naming, we will name it as potassium. We don't need to mention tripotassium. Only potassium is enough. Potassium space, since this is a, okay, we don't need to mention tris. Trioxalato is enough. Trioxalato, only one type of ligand is present. It's an anionic complex, so it is ferrate 2. Let's go with one more. Platinum NH3 Br Cl NO2, charge on complexes minus. Okay, we have 4 types of ligands here. One is amine, one is bromido, one is chlorido, then one is N-nitrito or nitrito N. To name this, we'll go alphabetically: amine, bromine, chlorine, then nitrito, A, B, C, N order. Okay, single one of them. So amine, bromido, we don't need to write capital letters, chlorido, nitrito N, since it is connecting with N, negative complex, so platinate. Charge we didn't calculate. Charge for NH3 is 0, bromine -1, chlorine -1, nitrito -1. X minus 3 is equals to -1, platinum charge which is equals to +2. And since it's an ion, it's an ion. This is the name. That's about naming the complexes. Let's see some peculiar names of double complexes. Both cation and anion are complexes. Nomenclature is not done. Example is Ag NH3 twice, then Ag cyanide twice. So first we need to name the cationic complex. If we assume this one is the cationic complex, because here there is a negative charged ligand, so this is probably the cationic complex. Let's start with this. Diamine, silver. The charge on this is the total charge of the complex, both double complex, is 0, but we have two variables here. If we assume this is plus 2, if the charge of this complex is plus 2, then this one cyanide minus 1 each, so minus 2. No, it is not plus 2. If we should assume it as plus 1, actually, plus 1, and this should be minus 1. If so, the charge on this one should be plus 1 because this is 0, and the charge on this should also be plus 1 because plus 1 minus 2 is equals to minus 1. 2 cyanides minus 2. Okay, now a little dash, dicyanido, since negative complex, argentate 1. Next, let's do one more. Platinum NH34, then platinum chloride. We can assume which has a neutral ligand is a cationic complex, and this to be an anionic complex. This should have a plus X charge, this should have a minus X charge. Only then the total charge would be 0. Since this charge is 0, the charge of platinum should be equal to X plus X. And this one, in this case, this platinum should have a charge of minus X minus the charge of to this platinum charge. Four minus X. So it's possibly 2. X, which is equals to 2. The charge on this is also 2. The charge on this is also 2. So this is a complex, cationic complex. We'll go with tetramine, positive complex. So platinum 2, then space tetrachloride, chlorido, platinate 2. Let's do two more of this, or one more. COCl2, NH3 four times. This thing thrice, and chromium CN6. Okay, this is a complex. We should name this complex. This is most probably the anionic complex. This is the cationic complex. We'll go with minus x here, plus x is the whole charge here. Actually, plus 3x, right? No, it is plus x itself. But it might be better to consider it as plus minus 3x here, plus 3x is here, and x is the charge of this one. So if we consider that, cobalt's charge should be plus 3, since it is having cobalt's oxidation state should most likely be plus 3, and since it is having two chlorides inside, so this charge is 1, then the total charge should be plus 3. Here also it should be minus 3. That means the charge on chromium is plus 3. Tetramine dichlorido cobalt 3, then space, we need to write it at the same line, but since I don't have that much space there, I'll write below. Then we have hexacyanido chromate anionic complex 3. Tetramine dichlorido cobalt 3 hexacyanido chromate 3. Now let's do one more complex. PTCl2 NH3 4, then PTCl4. This is similar to the second complex but a little different. Now this is the anionic, this is the cationic. Charge on platinum should be plus 2. It is good to remember this. Plus 2. So in this case the charge on this should be minus 2. Here the charge on this should be plus 2, because if it is plus 2, then minus 4, which gives minus 2 itself. Then if it is plus 2, then minus 2, it cannot give. It is having hexadenticity. Okay, then in this case it is minus 2. In this case the charge is plus 2. So x minus 2 is equals to 2. So charge on this should be plus 4. Platinum should be plus 4. If it is square planar, it is plus 2. If it is octahedral, then it seems to be plus 4. Since here coordination number is changed. Now this is the anionic complex. Let's name this first. Amine first, then chloride, alphabetical order. Tetramine dichlorido platinum 4, then tetrachlorido platinate 2. This is the name, tetramine dichlorido platinum 4 tetrachlorido platinate 2. The rules to write the formula of the complex, I'll just read them out. I won't write them, it takes too much time. Following rules are applied when writing the formula. First one, we need to list the central atom. We need to list the central atom. Like, I'll take an easier example here. Instead of a double complex, for example, in this case, first central we need to find a central metal atom. In this case it is cobalt. We need to find the central metal atom. Then ligands are listed in alphabetical order. Ligands, according to, it will be given in alphabetical order. First amine, then carbon atom. We should list it like this. In case of abbreviated ligand, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. If it's an abbreviated ligand like ethane 1, 2 diamine, then the first letter of the abbreviation, that is E, is used to find its position in the alphabetical order. The formula for entire coordination entity, whether charged or not, is enclosed in the square brackets. Charge on the entire coordination entity, it is enclosed in the square brackets. Like charge, it is mentioned here. There should be no space between the ligands and the metal within the coordination sphere. There should be no separation or space given between the ligands and the central metal ion. When the formula of charged coordination entity is written without that of the counter ion means this one. This is a counter ion, this is a complex. Like how to write the charges on the right subscript, here we should mention the charges, like plus or minus. If counter ion is not there, only we should mention the charges. If there is a counter ion, we should not mention the charges. That's the rules. Then coming to the one of the main next important topics, I won't be writing the formulas here, it is quite simple. Then coming to the next main topic, isomerism. There are many types of isomerism in this chapter, but let's see what are isomers. Two or more complexes having the same chemical formula but different in arrangement of atoms. Same chemical formula but different arrangement of atoms is known as isomerism. There are two types of isomerism. One is geometrical isomerism, I mean structural isomerism, and stereoisomerism. Structural isomerism. Then we have stereoisomerism. Under structural isomerism, we have types: ionization, isomerism, linkage isomerism, solvate or hydrate isomerism, then coordination isomerism. Under stereoisomerism, we have two types: geometrical isomerism, then we have optical isomerism. Okay, what is ionization isomerism? Complexes having the same chemical formula but they give different ions when dissolved in water are called ionization isomers, and the phenomenon is called ionization isomerism. For example, if there is CONH3 5 times SO4 Br and CONH3 5 Br SO4, when they are dissolved in water, these both have same chemical formula, but when this compound is dissolved in water, we will get Br minus and the coordination sphere. Here when this compound is dissolved in water, we will get sulfate and some coordination sphere. When they are dissolved, the ions formed are different even though they have the same chemical formula. Hence they are called ionization isomerism, ionization isomers, and this isomerism is known as ionization isomerism. Then coming to linkage isomerism, this is mostly shown by ambidentate ligands. Ambidentate ligands, complexes having the same molecular formula but different ligating atoms to donate electrons towards the metal atoms are called linkage isomers, and the phenomenon is called as linkage isomerism. Example we have, if we have CONH3 5 times NO2 and CONH3 ONO2 plus. Both of these have the same chemical formula and same atoms. But in this case, in the first case, cobalt is attacked by, or nitrogen will donate the electrons for cobalt. Nitrogen will donate the electrons for cobalt. But in this case, in the second case, oxygen will donate the electrons for cobalt. This is the linkage isomerism where it is shown by ambidentate ligands. Everything is same but the ligation or linkage between the central metal and the ligand is different. In the first complex, nitrogen donates electrons to the central metal ion. In the second complex, oxygen donates electrons to the central metal ion. What type of ion can give rise to ionization, linkage isomerism? Only ambidentate ligand. Ambidentate ligand. Now coming to third type, solvate isomerism. Solvate isomerism. Solvate isomerism is, let me give the definition, complexes having same molecular formula but different number of motor molecules in the inner coordination sphere inside the complex are called as solvate isomers or hydrate isomers, and the phenomenon is called as solvate isomerism or hydrate isomerism. What I mean by that is, for example, if we have chromium hexa aqua or hexa water Cl3 and chromium 5 aqua Cl2 dot H2O. Here in both cases, the formula is exactly same. Both of them have the same number of atoms. But in this case, there are 6 water inside. But here, only 5 water are inside. One water is in the form of like soil, water of crystallization. So this water is different. The number of water molecules inside the coordination sphere in both of these compounds is different. So these are called solvate or hydrate isomers, and phenomenon is called solvation or hydration isomerism. This is the solvation or hydration isomers. Now coming to last of structural isomers, that is coordination isomers. Complexes having the same molecular formulas but ligands are interchanged between the anionic and cationic entities of the different metal ions are called coordination isomers, and the phenomenon is called coordination isomerism. For example, we have chromium NH3 6 times and cobalt CN6 and CrCN6 and CONH3. These are coordination isomers. If we see in the first ligand, chromium is attached to ammonia. Here, cobalt is attached to cyanide. In the second ligand, even though the whole chemical formula is same, chromium is attached to cyanide and cobalt is attached to ammonia. This is interchange of the ligands between the corresponding metal ions. This is known as coordination isomerism, and these are called as coordinate isomers. This is about structural isomerism, where the structures differ, chemical formulas remain same. Coming to stereoisomerism. Stereoisomerism. What is stereoisomerism? Same molecular formula, but different spatial arrangement of atoms or ligands around central metal atom are called as stereoisomers, and the phenomenon is called as stereoisomerism. There are two types of stereoisomerism: geometrical and optical isomerism. There are note on, okay, let's see geometrical isomerism first. This topic of stereoisomerism is much larger than structural isomerism whole. Okay, let's start with geometrical isomers first. Stereoisomerism has two types. Stereoisomerism has two types: geometrical and optical. First, go with geometrical isomerism. Geometrical isomerism arises in heteroleptic complexes. Why? Because of in heteroleptic complex only it is possible, where different positions of ligands, the ligands occupying different positions around the central metal atom, gives rise to geometrical isomerism. There are two types in geometrical isomerism, like actually, okay, in tetrahedral or square planar, okay, we can say square planar. First type of geometrical isomerism is cis trans isomerism. Cis trans isomerism. There are two types of isomers: cis isomers and trans isomers. For example, if we take platinum, platinum, it is NH3, NH3, and the same platinum but with different arrangement. These are the two arrangements possible for the square planar complex of PtCl2 NH3 twice. Now, this arrangement where same ligands are adjacent, chlorine chlorine is adjacent, ammonia ammonia is adjacent, this is known as cis form, and this compound is called as cisplatin. And in case of this compound here, the same ligands are opposite to each other. Chlorine is opposite to another chlorine, ammonia is opposite to another ammonia. This is known as transform. This is known as, the compound name is transplatin. The ligands occupy either adjacent to one another or opposite to one another. This is called cis-trans isomerism. If similar ligands are adjacent to each other, the resulting isomer is called as cis isomer or cis form. If similar ligands are opposite to each other, the resulting isomer is known as trans isomer or transform. The complexes having coordination number 4 with square planar geometry and 6 with octahedral geometry usually shows this kind of geometrical isomerism, shown in square planar complexes and octahedral complexes. How in octahedral complexes? Example, if we take cobalt, Cl adjacent here, NH3, this is the cis form, or cobalt, this is the trans form. In octahedral, geometrical isomerism can be exhibited by geometrical isomerism. Note, geometrical isomerism, note point is exhibited by Mx2L2 square planar complex, Mx2L4 octahedral complex. These both exhibit cis-trans isomerism. Then there is one more type of geometrical isomerism that is exhibited by Mx3L3 octahedral form. This one will exhibit facial and meridional isomerism. This will exhibit facial meridional isomerism. As for what that is, I will explain it. There is one more note point before I'll explaining facial and meridional. There is note point is square planar complex of type MABXL. These are four different types of ligand. M is the central metal atom, where A, B, X, and L are unidentate ligand, shows three isomers, two cis, one trans. It is good to remember this information. Square planar complexes of type having four different unidentate ligands show three isomers, two cis isomers, and one trans isomer. Maybe it is if we consider something like this, and these might be two cis forms, and this might be the trans form. These are two cis forms. This is trans form. Then there is more note points. Geometrical isomerism doesn't only need monodentate ligands, it can also be shown with bidentate ligands. Also possible in coordination compounds having bidentate ligands of type MX. Example COCl2 En2. This we can show cis and trans like this. Something like this. This is a cis isomer. As for trans isomer, this indicates the double bonds. Now coming to facial meridional isomerism. It is a part of geometrical isomerism shown by M A3B3 type octahedral geometry. If three donor atoms of the same ligand occupy adjacent positions at the corners of an octahedral face, the resulting isomer is a facial isomer. If the position of the ligands around the meridians of the octahedron, the resulting the resulting isomer is called as meridional isomer. For example, if there is cobalt here, okay, let's write the complex first. Just a minute. Let's continue. I was about facial and meridional isomerism. Facial meridional isomerism. For example, we can show it using this complex. Cobalt. Okay, now here if we see, and these are two triangular faces formed by the for by ligands being adjacent by similar ligands. This is called as facial. They are forming a triangular face here. Facial isomerism or isomer. Then meridional, if we see, here this is meridional isomerism. Then few more note points. Geometrical isomerism is not possible in tetrahedral complexes having two different unidentate ligands because do not show tetrahedral complexes do not show geometrical isomerism because the relative positions of unidentate ligands attached to central metal atoms are the same with respect to each other. Let's write the note point. Tetrahedral complexes having two different or two or less unidentate ligands coordinated with central metal ion cannot show geometrical isomerism because the position of ligands, the relative position of ligands with respect to each other is same. Okay, that's about geometrical isomerism. Coming to optical isomerism. Optical isomerism. Isomers which are mirror images that cannot be superimposed on one another are called optical isomers or enantiomers. And phenomenon is optical isomerism. Then important term in optical isomerism is chiral molecule. Chiral molecule or chiral carbon especially is a carbon having four different groups attached to it. Or a chiral molecule is a molecule that cannot be superimposed. A chiral molecule is a molecule or ion that cannot be superimposed. Or the molecules or ions that cannot be superimposed are called chiral molecule. One more definition is given here. Chiral molecule, molecules which cannot be superimposed. Then there are two more terms, levorotatory and dextrorotatory. Two types under chiral molecule, levorotatory and dextrorotatory. Rotates, this levorotatory substance rotates light, plane polarized light to the left. It rotates the plane polarized light pass through it to the left. Dextrorotatory substance rotates the plane polarized light pass through it to the right. Dextro means right, levo means rotation to the left. This optical isomerism is common in octahedral complex having bidentate ligands. Optical isomerism, like it is common in octahedral complexes having bidentate ligands. Let's see some examples of optical isomers. These are good to be remembered. It's good to remember these examples. For example, COEN3 3 plus optical isomerism. This is a mirror. These are the, although the diagram is not very good, these are the two different optical isomers. If we superimpose them, if what does superimposing mean? If we place these two compounds or two mirror images over each other, they won't superimpose, they won't be superimposing. That is why they are optical isomers. This is a dextro isomer and this is a levo isomer. Then one more example, PTCl2 En2 2 plus. Platinum, These two complexes are also not superimposable. This is dextro, this is levo. Here only cis form shows optical isomerism. Most of the octahedral complexes with bidentate ligands will show optical isomerism, and the cis form will show optical isomerism. Trans form does not show optical isomerism as they don't have any non-superimposable mirror images. Then I think with that the isomerism is done. Coming to the next main topic, let's come to VBT, valence bond theory. Salient features. Central metal ion can use n-1d, ns, and np, and even nd orbitals under ligand influence to form hybrid orbitals that can accommodate the electrons received from them from the ligands. This is the first postulate. Shape or geometrical shape depends on hybridization. For example, SP linear, SP2 trigonal, SP3 tetrahedral, DSP2 square planar, D2SP3 or SP3D2 octahedral, DSP3 trigonal pyramidal or bipyramidal, D3SP3 pentagonal bipyramidal. The hybrid orbitals, okay, that's that second point. The hybrid orbitals of the metal. Hybrid orbital of CMI overlap axially with ligand orbitals to form sigma bonds or coordinate bonds between metal and ligands. Note, if n minus 1d orbitals are used for hybridization, it is called inner orbital complex. If nd orbitals are used for hybridization, it is called outer orbital complexes. If complex contains one or more unpaired electrons are present, it is paramagnetic. If it does not contain unpaired electrons, it is diamagnetic. Strong ligands like carbonyl, ammonia, cyanide causes pairing of electrons against Hund's rule. They are strong field ligands, and weak ligands do not cause pairing of electrons. I'll write the note points. N minus 1d used, inner orbital, Nd, outer orbital, unpaired electron, paramagnetic. If non-paired electron, diamagnetic. Strong field ligand, electron pairing. Weak field ligand, no electron pairing. Strong field ligand does not follow Hund's rule. Then that's about that. That's the postulates of VBT. Using VBT, we can also calculate the spin only formula, magnetic moment, using a spin only formula, which we got from the last chapter, D and F block elements. Okay, something if we have a doubt, Drew, like hybrid orbitals, we saw about hybrid orbitals here. Let's see the postulates again. CMI is central metal atom or ion can use n minus 1 d orbital, ns and np orbitals to form hybrid orbitals under ligand influence that will receive the electrons from the ligands. This will determine the shape. The shape will determine the hybridization. I mean, shape is determined by the hybridization of the orbitals, and hybrid orbitals of CMI overlap axially with ligand orbitals to form sigma bonds. And n minus 1 d, if the ligand uses n minus 1 d like prior d orbitals to form hybrid orbitals, it is called inner orbital complex. And if it uses outer d orbital complex, it is called outer orbital complex. If there are unpaired electrons, it is paramagnetic. If it is a strong field ligand, it will cause pairing. If weak field ligand, does not cause pairing. If pairing occurs, it is the crossing of Hund's rule, does not follow Hund's rule. Then, do hybrid orbitals actually exist? No, hybrid orbitals does not actually exist. Hybridization is just a mathematical manipulation of wave equation for the atomic orbitals involved. Just determines the probability, highest probability of where an electron can be found. Then coming to finally limitations of VBT, it involves number of assumptions, does not give quantitative interpretation of magnetic data, does not explain relative stability of complexes, does not explain color exhibited by coordination compounds, it does not give exact predictions regarding tetrahedral and square planar structures of coordination number 4. It does not distinguish between weak and strong ligands. Okay. First thing involves a lot of assumptions. It does not give quantitative interpretation of magnetic data. What does that mean? If we got the magnetic information like the magnetic moment of the individual complex, like a single complex magnetic information or magnetic moment we know, but totally we do not know the total magnetic information. Third one, it does not explain relative stability of complexes. The total stability of complexes is does not explain, how complex compound can exhibit color. It does not give exact prediction regarding shapes and structures. Like it can either be a coordination number 4 means it can either be square planar or tetrahedral. It does not exactly say if it will be square planar or tetrahedral. It does not distinguish between weak and strong ligands. Now coming to the next theory known as crystal field splitting theory or crystal field theory. Crystal field theory, CFT. This crystal field theory is an electrostatic model that describes the breaking of orbital degeneracy in transition metal complexes due to static electric field produced by ligands. Okay, they are saying it's an electrostatic model. That describes the breaking of orbital degeneracy in transition complexes due to static electric field produced by the ligands. Okay, Normally the d orbitals, it explains, normally all the d orbitals normally are degenerate, meaning they have the same energy level. But when ligand approaches the central metal ion, the ligand has a charge or electron pair which causes repulsion. Instead of calling repulsion, they said here the breaking of orbital degeneracy due to static electric field produced by the ligand. Static electric field produced by ligands is nothing but the repulsion caused by ligands. The steric hindrance or repulsion or static electric field, whatever it might be, due to ligand approach, the orbitals due to repulsion will have their degeneracy is broken. There will be some splitting in their energy. There will be an energy difference created in the degenerate orbitals. They won't be degenerate anymore. According to crystal field theory, according to crystal field theory, bonding between central metal ion and ligand is purely ionic or electrostatic. This is the first point. Second, ligands are treated as point charges in case of anions and dipoles in case of neutral molecules. Anions, point charges, neutral ligands, dipoles. Ligands are treated as such. The interaction between a transition metal and ligand arises from attraction between the positively charged metal cation and negatively charged or negative pole of the ligand. Interaction between CMI, central metal atom, and ligand is due to opposite or unlike charges. Due to this interaction, degeneracy of d orbitals is lifted and splitting occurs. We will see the splitting more clearly with a diagram. Due to this interaction between the transition metal and the ligands, degeneracy of d orbitals is broken and splitting of the d orbitals occur. The splitting of the we have five degenerate d orbitals. We have dxy, dyz, dzx, dx square y square, x square dash y square, and dz square. Dxy, yx, and zx are in the axis, of the, like in the, we have the three coordinate axes. In these axes, along these axes, the d orbitals are present. These are xy, yx, and zx. And the two x square dash y square and z square orbitals are present in the plane of xy and z plane. That's about the five specific orbitals or five orbitals of d subshell. The splitting of the 5 degenerate orbitals of metal ion into two sets of d orbitals with different energies under the influence of approaching ligand is called as crystal field splitting. The splitting of the 5 degenerate orbitals will split into two sets of d orbitals. One is T2g and the other is Eg orbitals under the influence of approaching ligands. This is called as crystal field splitting. The extent to which energies of these two sets of orbitals are split is called as crystal field splitting energy. The splitting is called crystal field splitting. The extent to which the orbitals are split the orbitals not orbitals the orbital energies are split is called crystal field splitting energy, denoted by delta. It is measured in terms of dq, a parameter called dq unit. It is a unit. The magnitude of splitting is arbitrarily fixed as 10 dq, so that delta, which is equals to 10 dq. The 5 degenerate d orbitals split into two sets of different energies. One is T2g and other is Eg. Three d orbitals dxy, dyz and dzx are oriented between the coordinate axis, are called T2g orbitals. The other d orbitals dx square dash dy square and dz square oriented along the axis are called Eg orbitals. The pattern of splitting depends on the nature of the crystal field. The ligands which cause greater crystal field splitting are called as strong field ligands. Okay, let's write the points. dxy, dzx, dyz, T2g orbitals between the axes. Dx square dash y square comma zz square, Eg orbitals along the axis, coordinate axis. Then if more crystal field splitting, strong field ligand less crystal field splitting, weak field ligand. The ligands which cause greater crystal field splitting are termed as strong field ligands, and the ligands which cause lesser crystal field splitting are called as weak field ligands. Okay, then let's continue. Let's see, we were about the crystal field splitting serine feature. It is an electrostatic model. The d orbitals normally are degenerate. According to CFT, bonding between central metal ion and the ligand is purely ionic. Anions point charges and neutral ligands are dipoles. Interaction between central metal ion and ligand is due to opposite charges only, is ionic interaction only. Due to this interaction, degeneracy of the d orbitals is broken and splitting of the d orbitals occurs. The splitting is called as central crystal field splitting. The extent of which the orbital energies are split is called as crystal field splitting energy, represented by delta. The unit is dq. The magnitude of splitting energy is arbitrarily fixed as 10 dq. Okay, delta is equals to 10 dq. The splitting the After splitting, the d orbitals are split into T2g, three T2g orbitals and two Eg orbitals. Dxy, dzx, dyz are T2g orbitals. They are between the axis in the planes. And dx square dash y square and dz square are Eg orbitals. They are along the coordinate axis. More the crystal field splitting, like the ligand which causes more crystal field splitting is called as a strong field ligand, while the ligand which causes less crystal field splitting is called as a weak field ligand. That's about the salient features of crystal field theory. Okay, there is one more thing, spectrochemical series, arrangement spectrochemical series. Arrangement of d orbitals, no, I mean not d orbitals, of the ligands in the increasing order of the field strength is called spectrochemical series. It is an experimentally determined series based on the absorption of light by the complexes with different ligands. That is why it is called as spectrochemical series. Depending on the wavelength of light absorbed, we can determine how much energy the the crystal field splitting energy is, the difference in energies. We can understand that. So it is called as spectrochemical series. The increasing order of field strength among some of the ligands are, the spectrochemical series is, the least is iodine, bromine, thiocyanide, chloride, sulfur, fluoride, hydroxido, oxalato, water, NCS, isocyanate, EDTA, NH3, EN, CN minus. Strongest is carbonyl. Strongest is carbonyl, cyanide, EN, etc. What is crystal field splitting? Crystal field splitting is the splitting of d orbitals into lower energy T2G set and higher energy EZ set due to the influence of ligands is known as crystal field splitting. Spectrochemical series is the arrangement of ligands in series according to the increasing field strength or splitting energy is called as spectrochemical series. The spectrochemical series is starting from iodine, the halogens, then water or oxygen compounds, then nitrogen compounds, then carbon compounds with carbonyl and cyanide being the strongest or stronger ligands. If we have to explain crystal field splitting in octahedral complexes, if we draw an energy curve, mean energy, we represent energy like this, energy scale. Normally, the d orbitals will be here. One, two, three, four, five. D orbitals will be here. This is free metal ion, the central metal. Then it will be increased. dxy, dyz, dzx, dx square dash y square, dz square. Now, average energy. This is average energy of d orbitals in spherical crystal field. This is the average energy. Splitting will be something like this. This is dx square dash y square, dz square orbitals. dxy, dyz, and dzx orbitals. This is the barycenter. This is the total splitting energy represented by delta naught or delta O representing octahedral splitting energy. This is 2 by 5 delta naught, 3 by 5 delta naught. This is the whole splitting of d orbitals. This is crystal field splitting. In octahedral complexes, the central metal ion is surrounded by 6 ligands. There is repulsion between the electrons of the d orbitals of the central metal and electrons of the ligands. The repulsion is more when the metal d orbital is directed toward the ligand and less when it is away from the ligand. So dx square dash y square and dz square orbitals are towards the ligand because they are in the coordinate axis, and because the coordinate bonds are sigma bonds, there will be axial overlapping along the axis. Along the axis meaning the more repulsion will be for the d orbitals which are along the axis, which are nothing but the dx square dash y square and dz square orbitals. So dx square dash y square and dz square orbitals, because they are towards the ligand, they will have higher repulsion and hence they will rise in energy. Their energy will rise, hence they experience more repulsion and will be raised in energy. So after they are raised in energy, these become less in energy, or like they don't become less in energy. We just saw this is the average energy and it will be below the average energy. And complexes are colored because when electron here jumps, absorbs light and jumps into these Eg orbitals, and when Eg orbital electron jumps below, they will emit radiations. Because of this, complexes are colored. dxy, dyz, and dzx orbitals are far away from the ligands, so they experience less repulsion and will move down in energy. Hence, in octahedral complexes, the 5d orbitals split into two sets, T2G containing dxy, dyz, and dxz orbitals, and EG set containing dx square dash y square and dz square orbitals. The difference in energy between T2G orbitals and EG orbitals is known as crystal field splitting energy. The difference is known as crystal field splitting energy. For octahedral complexes, it is denoted by delta naught, where O indicates octahedral. For EG orbitals, the increase in energy is 3 by 5 delta naught or 0.6 delta naught. For T2G orbitals, the energy will decrease by 2 by 5 delta naught or 0.4 delta naught. Okay, that's about crystal field splitting. Now, next concept is pairing energy. What is pairing energy? Energy required to pairing electrons. The energy required for electron pairing in a single orbital is called as pairing energy. What is the use of this pairing energy? If delta naught, that is splitting energy, is greater than pairing energy, then in case of, if there was a D4 configuration, it will split into EG and T2G, right? So normally, according to Hund's rule, we should go 1, 2, 3, and 4. But when delta naught, the splitting energy is so high compared to pairing energy, instead of splitting, the orbital will choose to pair here and it will become T2G4 configuration. Another case where delta naught splitting energy is less than pairing energy, for the same configuration D4, same configuration D4 again, here it will follow the Hund's rule. 1, 2, 3, and 4. If delta naught is lesser than P, the fourth electron enters one of the EG orbitals, giving the configuration T2G, T2G3 E1, this one T2G3 E1, EG1. Ligands from which delta naught is lesser than P are called as, the ligand causing this splitting is called as weak field ligand, and they form high spin complexes. This is a high spin complex. If delta naught is greater than P, in the first case, the fourth electron enters into the T2G orbitals, giving the configuration T2G4 EG0. Ligands which produce this effect are called as strong field ligands and they form low spin complex. Now coming to crystal field splitting in tetrahedral complexes. Same energy graph. Let's denote energy here. This is similar but slightly different. The d orbitals of the free metal ion, it will increase. We can denote a straight line. dxy, dyz, dzx. Now here this is e orbitals and this is t2 orbitals, dxy, dyz, and dzx, dx square, y square, z square. Total energy is represented as delta T. This is 2 by 5 delta T. This is 3 by 5 delta T. In tetrahedral complexes, the central metal ion is surrounded by 4 ligands. In presence of ligands, the d orbitals split into two sets: lower energy e orbitals containing dx square, y square, and dz square, and higher energy T2 orbitals containing dxy, dyz, and dzx orbitals. In tetrahedral field, the crystal field splitting is delta T. In tetrahedral complexes, the splitting of d orbitals is inverted compared to octahedral complexes. It is like reverse. For T2 orbitals, the increase in energy is 2 by 5 delta T, and for E orbitals, the decrease in energy is 3 by 5 delta T. Relation between delta T and delta naught for complexes having same metal and same ligand and metal ligand distances. Condition, there is a formula delta T which is equals to 4 by 9 delta naught. This under conditions that same ligand, same metal ligand interaction, distance, etc. For these conditions, same metal as well, same central metal, this formula is applicable. And here we used in octahedral splitting, we used a specific term T2G. This G represents Gerard, and it is a subscript used to denote center of symmetry. Center of symmetry. Octahedral Shapes or complexes have center of symmetry, but tetrahedral complexes do not have center of symmetry. Even for square planar complexes, we can use G subscript, but for tetrahedral which lack a center of symmetry, we do not use G symbol or G subscript. Here we see that there is no G, there is no T2G, there is only T2, and there is no EG, there is only E. Okay, coming to the next point, many tetrahedral complexes are high spin complexes, meaning they do not get paired up. It is rare for delta T of tetrahedral complexes to exceed pairing energy. Usually electrons will move up to higher energy rather than pair. Because of this, most of tetrahedral complexes are high spin. Most of tetrahedral complexes are high spin because most of the times delta T is less than pairing energy. Most of the time it does not exceed pairing energy. Because of that, it will mostly form tetrahedral complexes. We can explain color of complexes using CFT. I have explained slightly here. I'll just tell once more. When white light is passed through a solution of transition metal complex, the solution absorbs certain wavelengths of white light, and mixture of remaining wavelengths are transmitted as complementary colors. If blue is absorbed, red is emitted. If red is absorbed, blue is emitted. Complementary colors absorbed, the complementary colors are emitted. And where does this absorbed energy go? It is absorbed by the electron, and the electron will jump up into a higher energy level after absorbing the energy. Okay, that's about the color of complexes. Then coming to limitations of crystal field theory. Limitations of crystal field theory. First one, cannot explain color of complex with exception with full or empty d orbitals. The crystal field theory explained color of complexes as due to the splitting of the d orbitals, the electron jump from one orbital to another orbital, from T to G to E orbitals, and this will radiate and absorb energy. When they are coming from higher energy to lower energy, the electron will emit radiation. If it is going from lower energy to higher energy, it will absorb electron. It will absorb radiation. This will create the color of the complexes, and this is in the d orbitals. But if there are no electrons in the d orbitals, or if the d orbitals are completely filled with electrons, then this theory cannot explain the color of the complexes, as it is not possible for dd transition there. Second one assumes ligands as point charges So, according to that logic, anionic ligands should exert greatest splitting effect. But anion anionic ligands like halogens are found at the lower end of the spectrochemical series. What this means is that if we assume ligands has point charges, and we saw that like anionic ligands are considered as point negative charges, and neutral ligands are considered as dipoles. In such a case, if we consider anionic ligands as point charges, they should be the one to affect or to produce greatest splitting effect. But if we observe, that is not the case. We saw the spectrochemical series, the series where ligands are arranged based on their strength. In that table, anionic ligands are found at the weak field ligands like halogens. Most of the halogens, iodide, chloride, fluoride, bromide, all of them, these negative ligands are found at the bottom of the spectrochemical series, which indicates that they are weak field ligands. And normally that shouldn't be the case if we consider ligands as point charges. And one of the uh, limitation is derived from the salient features. Actually, we saw how they mentioned it only considered the complex as an electrostatic model and only considered ionic bonding and ionic interaction. So that means they did not consider account for covalent bonding between ligand and central ion. Okay, there are, with that, that is a limitations of CFT. First one, cannot explain color in full or empty d orbitals. Assumes ligand as point charges, but if so, anionic ligand should produce greater splitting effect, but that is not the case. Third one, covalent nature is not considered. Covalent bonding is also not considered. These are the limitations. Now, two more topics. Just a minute. Okay, let's continue. The next topic is metal carbonyls. What are metal carbonyls? What are metal carbonyls? Organometallic compounds in which carbon monoxide acts as a ligand. Organometallic compounds in which carbonyl or carbon monoxide acts as a ligand. There are some important structures in this topic that needs to be remembered. For example, NiCO4. This is a tetrahedral structure, something like this. Then there is pentacarbonyl ion. This is trigonal bipyramidal structure. Then we have chromium hexacarbonyl. This is an octahedral structure. Then we have manganese decacarbonyl. It is two tetragonal structure. I mean, two tetrahedral structures. Or wait, it is not tetrahedral. It is. I'll check it later. Then we have cobalt octacarbonyl. This has two bridging oxygens. And this one is a pyramidal structure. There are two pyramidal structures here. This one and this one. These are three pyramidal units constituting the cobalt octacarbonyl. And why we are seeing metal carbonyls separately is because they have a special bonding. Metal carbonyl has a specific bonding called as synergetic bonding. The metal carbon bonds in carbonyls have both sigma and pi character. Okay, let's see. Metal carbonyl bonding have both sigma and pi bonds. Metal carbonyl first bond is metal carbonyl bond. First we'll talk about metal carbonyl bond. Sigma bond is formed when carbonyl donates a lone pair of electron to vacant orbital in metal. This is the first sigma bond formation. When this is similar to how normal ligands donate electron pair. Here carbonyl also will donate one electron pair into the vacant d orbitals of the metal. This sigma bond is similar, nothing special here. The speciality comes in the pi bond formed. The metal carbonyl pi bond is formed by donation of pair of electron from filled metal d orbital into the vacant anti-bonding orbital of carbon monoxide. This is called as back bonding. Okay, special terms here. The MC bond, metal carbonyl bond, pi bond is formed by, here normally all ligands donate to the metal themselves. But here the pi bond is formed when the metal from its filled d orbital donates a pair of electron to the anti-bonding orbital of carbon monoxide. There are from MOT from previous class 11th, we saw that MOT there will be bonding and anti-bonding orbitals, molecular orbital theory. Anti-bonding orbitals are of higher energy, and this metal will donate electrons into that specific anti-bonding orbital of the carbon monoxide. This is known as back bonding, called back bonding, synergetic bonding, etc. This strengthens the metal carbonyl bond. This is called synergic effect. But due to this bond formation, normally when it is a single bond, carbon and oxygen in the carbon monoxide will have triple bond like this. So this bond is strong, this bond is weak. But when synergic bonding happens, it will become something like this. This bond weakens, this bond strengthens. This is the synergic effect, and that is about the metal carbonyls. Now, final topic. And if we have to draw a diagram, metal carbonyl That's a lone pair of electron. This is pi bonding. This is sigma bonding. This is pi star orbital. Synergic bonding. Now coming to the last topic, importance and applications of coordination compounds. The coordination compounds are of great importance. These compounds are widely present in the minerals, plant, and animal world and are known to play many important functions in the area of analytical chemistry, metallurgy, biological system, industry, and medicine. In biological system, if we have to say, we saw in the start of the chapter itself, chlorophyll, complex of magnesium, then hemoglobin, complex of iron, vitamin B12, complex of cobalt. Then these are the main ones. Among the other compounds of, okay, let's just read some importance. The pigment chlorophyll, responsible for photosynthesis, is a coordination compound of magnesium. Hemoglobin, the red pigment of blood which acts as oxygen carrier, is a coordination compound of iron. Vitamin B12, cyanocobalamin, there's a name, cyanocobalamin. The anti-pernicious anemia factor is a coordination compound of cobalt. Among the other compounds of biological importance with coordinated metal ions and are the enzymes like carboxypeptidase A, carbonic anhydrase, enzymes like enzymes are basically biocatalysts, carboxypeptidase, carbonic anhydrase. Carbonic anhydrase we have seen in respiration chapter. It helps in conversion of carbon dioxide into bicarbonate and vice versa. This helps in or facilitates the transfer or is transport of carbon dioxide. This the work of this enzyme is very useful. The conversion rates is thousands of times greater with the in presence of this enzyme. That's about biological system. Then qualitative analysis. Coordination compounds find use in many qualitative and quantitative chemical analysis. The formation of complex substances by using suitable reagents is very efficient and used in detection and separation of cations in qualitative analysis. The familiar color reaction given by metal with number of ligands, especially chelating result ligands as a result of formation of coordination entities. from the basis of their detection and estimation by classical and instrumental methods of analysis. Examples such as reagent include EDTA, DMG, alpha nitroso, alpha naphthol, cupron, etc. Used in qualitative and qualitative analysis, depending on color, etc. Used compounds are EDTA, DMG, which is dimethyl glyoxime, then alpha nitroso, alpha naphthol, then cupron, etc. used in qualitative analysis. Metallurgy, formation of coordination compounds during metallurgical extractions play great importance in metallurgy. Extraction process of metal like silver, gold make use of complex formation. Gold combines with cyanide in presence of water to form coordination compound uh, dicyanide orate in aqueous solution. In hydrometallurgy, gold can be separated in metallic form from the solution by addition of zinc. Refining of metal can also be achieved by the formation of complexes and then subsequent decomposition of that complex. For example, impure nickel is converted into nickel tetracarbonyl and decomposed to give pure nickel, that is called as Mond's process. First thing they gave is gold silver extraction. They gave especially gold extraction process. Gold combines with cyanide to give dicyanide orate, and this will combine with zinc will give pure gold. Then we have Mond's process, refining impure nickel plus it is converted into nickel carbonyl. This decomposed pure nickel. This is about metallurgy. Then for estimation of hardness of water, hardness of water can be estimated by titration with Na4EDTA. The calcium and magnesium ions present in the water will form stable complexes with EDTA. The selective estimation of Ca2 plus Mg2 plus ions can be done due to difference in stability constant of calcium and magnesium complexes. found by titration with Na4 sodium EDTA, calcium 2 plus and magnesium 2 plus form stable complexes with EDTA. They are individually estimated via the difference in their stability constants of their complexes. That's about estimation of water. Then 5 as catalyst. In many industrial processes, coordination compounds are used as catalyst. For example, Wilkinson catalyst, a complex of rhodium, is used for hydrogenation of alkenes. Wilkinson catalyst is chloridotriphenylphosphine rhodium, chloridotris triphenylphosphine rhodium. This is Wilkinson catalyst used in hydrogenation of alkenes. Then in electroplating, articles can be electroplated with silver or gold much more smoothly and evenly from the solution of complexes silver dicyanide and dicyanide argentate and dicyanide aurate than from the solution of simple metal ions. More efficiency by using that's about electroplating. Then in photography, the developed film is fixed by washing with hypo solution, which dissolves the undecomposed AgBr to form a complex AgBr plus 2Na2S2O3. Sodium thiosulfate gives sodium dithiosulfato-argentate. This is old technology. Now we have smartphones, so we don't need this. But still, let's learn about them. For washing undecomposed AgBr, we take AgBr plus 2Na2 S2O3. This is sodium thiosulfate. Gives Na3 sodium dithiosulfato-argentate. That's about the photography use. Then eighth use, presence of metals in toxic portion in plant or animal system can be removed by chelate therapy in medicinal chemistry. For example, excess of copper and iron are removed by chelating agents dipenzylamine and desferrioxime. B. Via the formation of coordination compounds. EDTA is used in treatment of lead poisoning. It's an antidote. Cisplatin inhibit the growth of tumors in cancer. This is medical chemistry. So I'll write it as medical chemistry only. Medicinal usage. Excess metals in animal systems, bodies basically, can be removed by chelate therapy excess iron or copper by chelating agents like dipenicillamine and desferroxime. B. Via formation of coordination compounds. Then EDTA used in treatment of lead poisoning. It's an antidote. Then finally, cisplatin inhibit growth of tumors. Basically, it will stop cancer. Let's see the total applications just once more. In biological system, chlorophyll is a complex of magnesium, hemoglobin, it's a complex of iron. We know both their uses. Vitamin B12 reduces pernicious anemia, like blood cells loss. It is a complex of cobalt. Enzymes which are very useful, like carboxypeptidase, carbonic anhydrase, all of them are complexes and are used in biological system. Chlorophyll, hemoglobin, vitamin B12, and enzymes like carbonic anhydrase and carboxypeptidase. These are the biological systems. Then qualitative analysis, EDTA, DMG, alpha nitrosol, alpha naphthol, cupron, etc. are used in qualitative analysis. They form through color and other estimations we can identify the specific substance. Then in metallurgy, gold and silver extraction, it is very useful for using complexes. First, gold is reacted with cyanide to give a specific complex, that is dicyanide orate, and this will react with zinc to give pure gold. Then there is for refining process, Mons process, where impure nickel will react with carbonyl to form complex tetracarbonyl nickel. This will get decomposed to give pure nickel. This is the refining process. Then estimation of hardness of water, we can estimate it by titration with the Na4EDTA. And these calcium and magnesium salt, which are the main reason for the hardness of water, will react with EDTA to give complexes, and there is different stability constant for these two complexes. So based on that, they will estimate the amount of calcium and magnesium in the water. As catalyst, Wilkinson catalyst, which is tris triphenol phosphine chlorido rhodium, used in hydrogenation of alkenes. It is also used, they are also used in electroplating. It is more efficient to use dicyanide orate and dicyanide argentate for electroplating. It is much more smoother as well for electroplating of articles, jewels, etc. Jewelry. Then photography for washing undecomposed AgBr. AgBr plus sodium thiosulfate will give a specific complex and NABr. Medicinal, it is used in when excess metals are present in animal systems. It can be removed using chelate therapy. Excess iron and copper by dipenzylamine and desferoxime B. EDTA is used in lead poisoning. Cisplatin is used in inhibiting growth of tumors. Let's read just once more. Biological system, we have chlorophyll, hemoglobin, vitamin B12, and enzymes. Chlorophyll is a complex of magnesium. Vitamin B12 is a complex of cobalt, reduces pernicious anemia. I think its name is cyanocobalamin. And hemoglobin is a complex of iron. Then enzymes such as carboxypeptidase and carbonic anhydrase are very useful. Qualitative analysis, EDTA, DMG, alpha nitrosol alpha, naphthol, cupron, etc. are used in qualitative analysis. Metallurgy processes for extraction of gold. Gold and silver will react with cyanide to form dicyanide orate complex. This will react with zinc to give pure gold. Then in refining process, Mons process, where impure nickel will form a complex tetracarbonyl nickel, and this will react with, this will again get decomposed to give pure nickel. This is the refining process. Then for estimation of hardness of water, when titrated with, when the water is titrated, when the specific sample of water is titrated with Na4EDTA, we can estimate the results as the magnesium 2 plus and calcium 2 plus ions will form complexes with different stability constant with EDTA, and due to these differences we can estimate the amount of calcium and magnesium ions present in this water, in the specific sample of water. Then we have catalyst, Wilkinson catalyst, which is used in industrial processes to manufacture alkenes, or like to, for hydrogenation of alkenes, not manufacture, for hydrogenation of alkenes. The Wilkinson catalyst is chlorido tristriphenylphosphine rhodium. It's a rhodium complex. And once more, the uses, it is used in hydrogenation of alkenes to alkenes, or whatever it might be. They just gave hydrogenation of alkenes. In electroplating is much simpler and efficient and smoother when using complexes such as dicyanide orate. In photography, for washing the undecomposed silver bromide, it is washed with thiosulfate, sodium thiosulfate to give specific complex and NABr. Then in medicinal chemistry, chelating therapy, which uses complexes to remove excess metal ions, metals which are present in the animal systems or bodies, which can be toxic. Excess iron and copper can be removed by depenicillamine or desferoxyxime, desferoxime, ferrioxime B. These two names are a little hard to remember. Excess iron and copper are removed by depenicillamine and desferrioxime, desferrioxime B, depenicillamine and desferrioxime B. Okay, EDTA is used in treatment of lead poisoning. Cisplatin is used in treatment of cancer or inhibiting the growth of tumors. That's about coordination compounds. Most of everything is covered. Okay,